So the actual long title of this talk was Comparing Machine Learning Techniques and Traditional Time Series Techniques for Financial Series Prediction, but I couldn't fit that in. But this is, so I'm going to talk about this. So go through a bit of background first, what you need to know, and then talk about an ARIMA model, which is the traditional technique that I used, talk a bit about machine learning in finance, a bit about what I wanted to know. So I did this as a research piece for my master's degree at the University of Surrey, and that was in economics and finance. And then talk about how I implemented the models that I used, talk about how I compared the predictions, then go through the empirical results, a bit of discussion about the two techniques, and then my overall conclusions. So start off with background. So prediction of financial markets has been a topic for discussion as long as financial markets have existed. If you can better predict financial markets, then you can make more money. But also, if you can better predict, then you can better understand what's driving these markets, and then you can better predict downturns, and then once you can predict downturns, you can better prepare for them. So I'm going to start off with this quote from Eugene Farmer. To what extent can the past history of a common stock's price be used to make meaningful predictions concerning the future price of the stock? So there were two answers to this question by both Chartist theories and random walk theories. So Chartist theory assumed that all the information you needed was in the stock movement, that history repeated itself, and these stocks were a series of patterns repeating. So once you understood the pattern, you could then use that to make predictions and make more gains. Random walk theory, on the other hand, said that these financial series were no more predictable than a series of random walks, and you can't use the past to predict what the future is going to be. But actually, for this, we're going to actually stick with random walks, which seems a bit of an odd choice. But if we then take a look at the efficient market hypothesis along with our random walk, things start to make a bit more sense. So the efficient market hypothesis states that, the current stock prices always reflect all available and relevant information. So if, for example, someone hears that a company is going to be doing well in the future, they'll go out and buy stocks for that particular company, which is a sort of self-fulfilling prophecy. So because everyone's buying into this company, the company ends up doing well just because they've heard information that it will be doing well. And conversely, if someone hears that a company is going to be doing bad, then it sort of self-fulfills and the company ends up doing bad. But this entry of this new information that people are trading from is unpredictable. So stock prices that are changing in response to this information are therefore unpredictable and move as a random walk. So then do we want to test that actually what we're dealing with is a random walk? So we've got the two charts. The chart on the left is a true, pure random walk with just, it's as likely to go up as it is to go down. The example on the right is a random walk with drift. So as well as a random walk, it's also got a linear time trend in there. But as there's no clear direction of which way the random walk is going to develop, it could move away from that trend. But overall, there is a linear trend in there. So testing for random walks. So a random walk is said to be a series with a unit root, and it has a unit root of 1. So initially this testing for random walk was done by eye. People would look at the chart and just say, oh, it looks like a random walk. But then Dickey and Fuller created a test which became known as the augmented Dickey-Fuller test. And then once you've run the test and it tells you it's a random walk, you can then deal with that random walk. So to deal with random walks, we use differencing. So differencing is instead of working with the raw values, working with the difference in a certain time step and the time step before it. So we work with the difference value instead of the raw values. The downside to this solution is that you lose one piece of data every time you have to difference, but that's usually a small price to pay. So then once we've dealt with our random walk and we've rendered the series, what would be known as stationary, so the mean is stationary and the variance is stationary, we can then move on to fitting our models. So this takes me to the first technique that I use, which is the traditional technique, which is the ARIMA model, which requires data to be stationary. It can't work with non-stationary data. So an ARIMA model is auto-regressive integrated moving average model. And it's a basic time series technique, and it's been used to predict future trends in finance. So the ARIMA model captures an autoregressive part and a moving average part. So the autoregressive part uses basically how do prices yesterday affect what the price will be today of a particular stock. And then it includes a moving average, which is how the noise from past, how does sort of the noise value from past prices, how is that reflected in what the price is today? And then the integrated is the order of differencing that you had to do to render your series stationary. And then, so the second technique is machine learning, which I was comparing. So machine learning is especially supervised learning, is very well suited to finance because finance just has has a wealth of accurate historical data that it can draw upon, which is, great for supervised machine learning. But current applications of machine learning in finance include algorithmic trading, so or automated trading. So how can systems that monitor stock prices and then can make a decision on whether to buy or sell. Fraud detection, so as ways of committing fraud becomes more sophisticated, so must the systems preventing it. So these systems now need to be able to learn and adapt to new threats. And then loan approval, which as loan companies have a huge wealth, a huge amount of historical data on who's been approved for a loan, how much they had to pay, how did they default, that sort of thing, so they can learn from that and then decide should this person be approved for a loan or should this person not, how much do they have to pay. But what I wanted to do was then apply machine learning to financial series prediction as opposed to the types that we've got here. So the research questions, what exactly I wanted to answer was, one, can a machine learning model outperform an ARIMA model, financial series prediction? So comparing tests for superior predictive ability for each of the two types of technique. I also wanted to take into consideration run speed. As an extreme example, an analyst may not want to wait 3 days for a 90% accurate result when they could get an 80% accurate result in 2 hours. As an extreme example. And so faster model runs would also give an analyst time to then perform additional analysis and gain additional insight. And then secondly, my second question was, can a machine learning model provide any additional insight over an ARIMA model, whether it can outperform or not? So first, the data that I was working with. So a financial series is simply shows the price change in a particular market segment. So I worked with the S&P 500, which is an American stock index of 500 large companies, which has stock listed on New York Stock Exchange and the NASDAQ index, and it's weighted by their market share. And I used data from the 50s to earlier this year, and then the FTSE 100, which is the UK equivalent, and I used data from 2001 to earlier this month. The reason I used two data sets was that existing literature used the S&P 500, so I wanted to compare my results with existing literature and then compare them with another data set, which was the FTSE 100. So then the implementation, Python. So why I used Python was that it just has extensive, well-documented libraries for statistics and machine learning, well-documented being key. So some of the libraries that I use are stats models, which is great for metrics once I had my models, and then for implementing the ARIMA model. Scikit-learn is a great library for basic machine learning implementations, and then I used Keras as an interface to TensorFlow, which is a sort of lower level machine learning library. Pandas, which is probably the best library ever in Python, which just makes working with data so much easier. My brother's a big MATLAB fan, and he's like, oh, you could do this really easy in MATLAB, but I'd say with Pandas, Python is just as good with matrices and big data sets. Matplotlib, which is easy to use graphing, and then the timeit library, which I used for comparing run speeds, which is really good for just comparing small snippets of code, so I could just put start time, end time, it sort of wrap around my model runs and then compare how long it took. But my number one reason for using Python was Jupyter Notebooks. So I thought that they were a really great way to provide the code along with my dissertation. So I was providing it, my dissertation was submitted to the School of Economics. So they're not big on Python programming. So I could provide a notebook along and show exactly what I've done, how I've done it, that sort of thing. So that was, my number one reason for using Python. So then the models, my code's available on my GitHub page, and this is the bit sort of that I've left out to keep this talk within the 25 minutes. So through going through a process of fitting models and comparing their goodness of fit, these are the models that I selected for comparison. So I selected for the S&P 500 an ARIMA 210, which is an ARIMA model with two autoregressive components, one order of differencing, and it actually turned out that I ended up with no MA components, which was a bit odd, but comparing criteria, that was the best model that I got. A simple support vector machine, a simple neural network, a simple recurrent neural network, recurrent neural networks are really good for this, as they're designed to capture sequence information. So previously, neural networks would treat every input as independent, but the recurrent neural network treats your data as a series, as the time series requires. And then there's each layer in your network has a hidden state, which acts as a memory of the network, and it holds information from previous time steps so that can be used for your current time set. And then I specifically used a long short-term memory flavor of recurrent neural network, which has the same structure as the recurrent neural network, but uses a slightly different way of calculating this hidden state, which is more efficient for long-term dependencies, which was great for the data that I had. So in terms of comparing predictions, there were several ways of comparing prediction. The existing literature that I took a look at used simply a hit ratio of whether each model predicted in the correct direction, as opposed to actually taking by what amount it predicted in the correct direction. But there are other ways of comparing predictions. So one of the things I wanted to do was take a range of comparing predictions as opposed to the one hit ratio that they used. So each of them has pros and cons though. So root mean squared error just gives a sample average of the difference between the predicted value and the observed value, but it can be sensitive to outliers. Mean absolute error and mean absolute percentage error, similar, except mean absolute percentage error uses percentage, and it can be biased towards models that underpredict. Thiel's U statistic gives a ratio of a model's mean squared error and then compares those mean squared errors to a benchmark model. So you're comparing each of your models against this primitive benchmark, and it returns a value. And then there's the Diebold-Mariani test, which goes one stage further. So once you've got your comparative statistics, it then says, are these forecasts actually significantly different, as opposed to one just being better than the other? Is it statistically better? And then weighting predictions. So in financial series, it might be better to weight under prediction better than over prediction. So predicting the direction of the result, whether positive or negative, rather than the size, it could be more costly to under predict than to over predict. So that's a way you can compare your predictions. So then I wanted to discuss, actually, before I looked at the empirical results, actually which model was easier to fit and what it was good for. So the ARIMA model was quite transparent. It was very clear. Once you had fitted the model, you could see exactly how the terms were interacting, whereas the machine learning algorithms weren't as clear as that on the face of it. So once you fitted the model, you can then examine the summary statistics and investigate residuals very easily, which was not as easy with the machine learning models. But some cons were establishing the order. So establishing the order of an ARIMA model can be quite difficult. So I sort of had a feeling of unease that I'd picked a set of models, and I could quite easily pick which was the best model out of that set, but was the set that I had the best set to be choosing from. It was sort of like picking the set by trial and error, which wasn't too great. But then once you've established your order, the ARIMA model was much easier to fit. You just say, give me an ARIMA 2, 1, 3, or whatever, and it will give you that. And the run speeds are the run speeds were fast. It never really got beyond 1 second to run the ARIMA models. But was it appropriate was one of the questions that I asked once I saw the empirical results. But yeah, pros and cons of the machine learning models were that I had access quite easily to a wide range of methods, so especially using the scikit-learn library. The only cons are it's viewed as a black box method. You just say, give me a neural network, give me some outputs, and what actually is it doing is not so obvious to perhaps some analysts, so they might be uncomfortable trusting the machine learning model. I could have used non-stationary data with some machine learning models, so I wouldn't have had to go through the whole is this a random walk process at the beginning. The machine learning models I used did need stationary data, but there are ones that don't. The run speeds, the models that I run actually ran quite fast, but I did go through a process of optimizing my recurrent neural network, and when I was testing what should my correct batch size be, what should my correct number of epochs that I want, that in testing that sometimes they got really quite long, going from a second to run the simple recurrent neural network up to an hour or so to run one where I'd adjusted some of the parameters. So I've put hyperparameter optimization as a pro and con. So while it is great to be able to adjust your model and get it to fit your data better, you can get bogged down on tweaking, just, oh, maybe I want just maybe one epoch more would be better than one epoch less, that sort of thing. So you can get bogged down, and you sort of, for a beginner to machine learning, that can get maybe perhaps a bit overwhelming. I think with time, once you use machine learning models and you're like, oh, I've used this on a similar sort of data set, this was the, this set of hyperparameters looked good, then it would get a lot easier. But for someone who's a beginner, I thought the ARIMA model was a lot easier to run. But neither model works by magic, and the model was, both of them are only as good as the data that you're going to put in. So the empirical results, so this is the data that came up for the S&P 500. The R-squared is a goodness of fit measure, and my simple support vector machine has a negative R-squared, which was really bad. The data just, it just wasn't really well suited to it, and that was running a vanilla support vector machine. So I guess, again, with tweaking hyperparameters, I probably could have got something that was a lot better, but I discounted that as perhaps inappropriate. And then if you take a look at the mean squared error and the mean absolute error, just the ARIMA model performed comparative with the neural network, but really with an R-squared that barely covered 1% of the data, was it really an appropriate comparison, as the recurrent neural network outperformed it considerably. So that was my conclusion, that the machine learning model, especially, well, the recurrent neural network, if we just keep the support vector machine out of it, the recurrent neural network vastly outperformed the ARIMA model. But for this data set, perhaps an ARIMA model was not an adequate fit. Past literature did compare ARIMA models and various machine learning models, which is why I went down that route. But I think perhaps if I was to do it again, I would try an ARIMA model in conjunction with perhaps another time series techniques, like a GARCH, which is looks at conditional variance as well as the ARIMA conditional mean. And perhaps that would be a more appropriate comparison. But existing literature said that the machine learning models were vastly superior to the ARIMA model, which I agreed with. The machine learning models didn't have a significantly long run speed to justify using the poor ARIMA model. And then additional insights, I thought that as the machine learning model provided better predictive accuracy in the same amount of time, you could gain additional insights by what you could do with the time that you've saved by having a better predictive model. And then being able to use that time to collect more data or combine with other machine learning techniques, so taking a look at sentiment analysis from Twitter for the various stocks. Yeah, so that was my research, comparing machine learning and an ARIMA model for financial series prediction.
Well done. Thank you very much for a great talk. Do we have any questions?
How do you think the fact that people are running predictive models on stock prices actually affect the stock prices in the future?
So people actually
people who are interested in investing in stocks
Yep.
are using predictive models to
Yep.
understand how to invest. How does that feed back into the prices of the stocks?
So by running models, so people being interested in running models, how does that affect the price?
Well, people who are interested in investing in the stock market
Yep.
are running models
Yep.
to tell them how to invest.
Oh, okay. So
So
if
that's
yeah. So if
feedback.
If their models are under predicting, and saying it's something's not going to do as well as it might do, then yeah, that can have an effect, because then people will think, oh, this company's not going to do as well. So then if, like in the spirit of the efficient market hypothesis, if they're then not investing, then it's not going to do as well as if it might have done without these models predicting for it. So yeah, it could have an effect.
I don't know if I understood this correctly, but you mentioned the efficient market hypothesis,
Yep.
and you mentioned a charted model, I think technical analysis.
Yeah.
Why did you discount the technical analysis model in your sort of project?
The reason I did that is because I wanted to focus on the journey to go from efficient market hypothesis to random walks to rendering my data stationary for use with the ARIMA model. So if I knew that I was going to use an ARIMA model, so that's why I discounted that, because I at the beginning decided I was going to use an ARIMA model.
So I have one question. I'll get to you then. You are using stocks, I believe, because of the stationarity requirement of your methodologies. Have you thought about looking at other time series of other phenomena?
Yeah, so I picked time series financial data just as I was doing an MSc in economics and finance, and thought I should probably choose a data set in that area. But yeah, it could be expanded to other time series techniques, comparing maybe an ARIMA model, because ARIMA models are very flexible. Perhaps if you find a data set that ARIMA model is really good at predicting, comparing that with a machine learning model and seeing how much can you actually get out of the machine learning models compared to something that ARIMA is really good at. And why you would do that is because then that would drive you to what additional insights can I get out, because where my ARIMA model wasn't as good as my machine learning models, I was content that I was getting better predictive accuracy. Where if your ARIMA model is really good at something, then it can drive you to then try and make your machine learning models better and use them in better ways, and gain additional insights and maybe discover something new that no one's seen before.
Okay, thank you for the great talk. I may have missed that. What frequency of data do you use?
Oh, I was using daily data.
Daily data,
that
is
was a thing that it might be interesting to look at intradaily trading as well.
Yeah.
But I use daily data.
So then what is the prediction horizon? How long do you predict when you compare different models?
I separated the data into the first 75% was used as training, and then the last 25% was used for testing. So I tested on the last 25% of my data, which for the S&P 500 was quite a large range. For the FTSE 100 was a couple of years.
Okay, so including short and long horizon, you mean, is it? When you do the prediction.
Sorry, I can't quite hear you.
So when you do the prediction, then you
Yep.
include both the short and long horizon, is it? So not just predict one day
no, I
ahead,
used-
but also maybe
yeah,
a few weeks later, or
Yeah, the predictions that I was making were daily as well. So I was
Daily.
looking at a short horizon as opposed to long-term trends.
Great. I think that's all the time we have for questions. So, but I'm sure Hannah, if you can find her, would be happy to talk about it more with you. And otherwise, let's thank Hannah finally for her talk.